Hi, and thank you for coming to my talk. My name is Sky, and my collaborator Millie Mintz, as well as my professors Alex Ororbia, Cecilia Allman Reynolds Bailey, are part of RIT's REU for Computational Sensing for Human-Centered AI. And our project is on implementing a confusion detecting cognitive agent. So from online learning to chatbots and virtual assistants, complicated emotional interaction between humans and robots is on the rise. And there becomes a need then for the classification of emotions by robots, by which we mean the prediction and emotional empathy to infer human feeling from our speech, our prosody, and our faces as we interact. Emotional classification via these sensory inputs has been studied, but confusion as an emotion or as a cognitive state has been more difficult to pin down, given that it is a largely internally realized feeling and implies a much wider range of expressions. And thus, work towards computer classification of confusion is more nascent. Our research questions for this project then are: one, can we build a model that effectively classifies confusion either unimodally, just through speech, audio, or text, or multimodally by combining those different features? The question I will be focusing on in this talk is which features of multimodal dialogues between the speech or prosody, the transcribed spoken utterances, or the facial expressions aid in the classification of confusion. Our other two questions were: how does the intensity of confusion, whether a person is not confused, less confused, or quite confused, or very confused, how does this intensity change the predictions of confusion on such data? And the fourth question is, can we build a neural network that learns feature importance for itself, that performs better than a more naive classifier, which would be a more interpretable model, but potentially a less strong classifier? To this end, we engaged in our own human subject study. We did data collection with 20 participants, recording them on Zoom. We had pairs of participants interact with each other to get exaggerated facial and audio data. And what we had them do was engage in the discussion of and solution of various challenging tasks. Task one, which we'll see in a moment, had them attempt to use calendars to find a date in common when they could have a meeting, when both of them were quite busy. And the other two tasks involved discussing and trying to find the solution of various difficult logical riddles. We can see here that, as intended, these tasks evoked different levels of confusion, ranging from the first task largely being not very confusing to the later tasks being a bit confusing to quite confusing. Then had participants use a website which we built to annotate their confusion throughout. Doing this, they would watch a playback of themselves solving the task, and below the video would be buttons indicating their level of confusion, which they would change as their level of confusion changed, giving us a frame-by-frame annotation of how confused the various participants were at the various times. We then pre-processed this data very heavily through several open source feature extraction programs. The main two we used for audio and video features were OpenFace, which is an open source program that generates the various facial action units. So measures between 0 and 1 of the different minute building blocks of various facial expressions. For audio features, we processed with Audeering's OpenSmile, which extracted various features of the timbral characteristics of speech from the voice probabilities and fundamental frequency to the Kepstrel coefficients at various intervals along the MEL scale. This was done for each participant separately. Zoom very handily outputs video features for both participants separately. and OpenSmile was able to differentiate the two faces in the video we fed it. In addition to these, the confusion labels from the confusometer, which was previously shown, were then used to train the model. Additionally, we wrote another script which extracted various features from the transcribed text. After feeding the audio recordings into Amazon Transcribe, we were able to use a library called Deep Disfluency, which marked up the text. From here, we used these combined features, which were then aligned by each token, to train a hidden Markov model. Now, a hidden Markov model will learn something called a Markov chain, which is realized as a matrix describing the probabilities that various states will move to one another. This is based upon a fundamental assumption that the state of a sequence of observed variables at any given time is only dependent on the very previous state in the sequence. And so a Markov chain at its very basic can be seen here. We might have, for a simplifying assumption, let's just say we had two labels, confused and not confused. We would then have a sequence of observations that in this moment versus that moment, a participant might have been confused or not confused. And the arrows between the various nodes then indicate the probabilities that given the current state is not confused or confused, how likely it is that it will transition to the other one. The beauty of a hidden Markov model is then we can use this transition matrix to infer the transitions between what are called hidden states. So we infer patterns in variables which we weren't able to directly observe. And in that case, those are our various features, like the facial action units, the audio features, or the transcribed text ones. So a hidden Markov model then takes a transition matrix and learns what's called the emission matrix, which is the probabilities, the likelihoods of each feature occurring, given that the confusion in this case is in any given state. Given actual observed data, the HMM can then use the transition and emission matrices to predict the hidden state sequence causing the observed events and thereby generate new data, or to, given actual observed data, calculate the likelihood of that data appearing. In our case, our model is a Gaussian hidden Markov model, meaning that assuming a normal distribution of features about the calculated means from the emissions matrix, our model is capable of calculating feature likelihoods. The library we use to realize this model is called HMM-Learn, a link to which can be found here. So, to get our results about feature importance, we can simply look at the emission matrix, which in our Gaussian HMM model is realized as mean likelihoods and variance in likelihoods of each feature given each confusion state. Using that, we can plug our actual observed data that we gathered from our participants into a Gaussian distribution using those two parameters as the means and the variance, average across time step, and then average across various participants to establish the top features given each label. And what I've presented here are the highest meaned features for the very confused label, and the bars indicate their standard deviations. And we have some interesting results. All in all, the top features here, largely speaking, are changes in the prosody and timbral characteristics of a person's speech. A number to highlight are these two here, which are the zero crossing rate and root mean squared energies first order deltas. So changes in the intensity with which someone speaks. Another here is the fundamental frequency, the change rather in the fundamental frequency, and a number of changes in the various Mel frequency Kepstrel coefficients, which indicate intensity in different spectra, and together can indicate the timbre of a particular moment of speech. A few others that seemed very important are interregna and reparanda, from people making disfluent utterances. So correcting one's speech is predictably a good indicator of confusion. And notably, AU23, which is the lip tightener or some such. So moving the corners of your mouth in. We found that that was a very common expression made while confused. We can also gain important data points by looking at the bottom means. So what we found to be some of the least important, interestingly, were questions. People in these tasks seemed to ask questions both when they were confused and not, which I suppose is natural when communicating about puzzles. And a number of the facial action units which are related to shock, such as raising the eyebrows and opening the eyes and opening the mouth. People didn't tend to make those intense expressions while confused, preferring rather to make more careful facial tightening actions. So the limitations in future work here might be to increase the data set size. We only had 20 participants, which taken all together only gives us about 6 hours of facial, audio, and text data all in all. Another is the nature of this hidden Markov model's assumption. Given that we can only use the previous state to determine the next, we're somewhat limited in the amount by which we can measure events that last longer. If we were to only analyze by individual frames of audio, say, the time step would be far too small for the assumption to make sense. In this experiment and in these data were based upon average features from each token. So while our time step is larger, it still isn't large enough to capture changes in confusion over the course of speaking a whole sentence. And with more data, we might well be able to set up a model that takes that more into account. We also could do to hybridize our HMMs to handle discrete data versus continuous data and experiment with different feature sets. Perhaps there are features that we've gathered here that aren't very good and are simply clouding the model rather than adding anything. And in order to answer our last research question, especially, we believe that a much better classifier will be to implement a recurrent neural network, which would truly be supervised, whereas a hidden Markov model really only is semi-supervised, inferring the nature of the actual labels only from the transition matrix. Thank you so much.